Okay, then Nicolas already installed Skywave. To install it, it's a standard Windows installer, and to get it is easy. You can go to the portal innovationsforesight.com.
David, first question.
Yes.
From your point of view, is it better to install Skywave on the imaging PC directly, or it doesn't matter? I can do also do it on my home PC.
You can do on your own PC, because sometimes doing image analysis, it takes some CPU resources, and
Okay.
sometimes it's better to have on your own PC.
Okay.
But what you can do, what I do very frequently, is sharing a folder between the two PC. And then you can, if you use Nina, for example, you can save the snapshot inside the folder. And then with Skywave, I will show that later, you can spy the folder, and when a new image is coming, it's automatically loaded and analyzed. Then you can stand on your telescope turning the knobs, and with a loop, you can see the upcoming images, and then you can see what you are doing on the scope directly without having to interrupt or go down from the scope to touch your keyboard. You can just watch the screen and turn the knobs. That's the idea of this. And to do that, we share a folder between the two applications, and we write each data inside the folder. And you turn, for example, you wait some seconds, turn the knobs and wait the result, see the correction, and adjust and go further until you reach the good result. Then first, to install, you have to go on this site, and then you can download the installer. Of course, normally we still have the 32-bit, but it's not recommended. That's why it's black here. You have to install the 64-bit. It's better. And then when you install it, you get this icon on your desktop. And at the first load, you have to register a license. And which name I use, Nicolas? Your names or Alex or
Alex.
Alex.
Alexandre, what is your?
It's I don't remember. I don't remember. It's Itik or?
Oui, yes.
And your email, it's Alex Itik.
Oh, non, Alexandre.
Alexandre.
Itik
at
free.fr.
Okay.
J'ai déjà demandé des licences. J'ai essayé de le.
Il me semble que j'avais vu.
Ouais, mais j'avais vu avec Gaston. J'avais jamais réussi à le faire fonctionner avec Nina.
Ok.
Sorry, Thomas. I just already asked for license for Skywave, but.
Si jamais Gaston, il parle très bien le français. Hein.
Oui, je lui avais. On avait échangé en français, mais j'ai pas réussi à faire marcher avec Nina. Enfin, avec Nina en tout cas.
Okay. Then now, normally for astro amateur, the level it's collimator. It's limited. The Pro is designed for example, a scope rental farm, the same that you have in Trevinca, or some of them that are also in Chile or also in Africa. And there is much more functionality. For this demo, I will take the Pro version because there is much more. But the main things remain the same. There is less plots, less viewports, and less functionalities in the collimator, but it's enough to make the alignment of the mirror with the collimator version. And then I have to activate the Pro. Okay. And I will register. Second things that we have to do is to define a working folder where we store all the log files and things. By default, we can go on the document and create a new folder, for example, Skywave. And okay, then once it's done, it opens. Yeah, you can check the release note. It's auto. There is an auto updater which check on the net on the internet if there is a new release, and then you can check the release and what's new, and you can also create an account on the portal to manage your models and things like this. For this demo, we will not use an account. We go offline. Skywave is working completely offline also. If you have a observatory without internet or with poor internet connection, you can use it. There is no need to. It's completely offline, working offline. Second things that you have to do is to define your instrument. Then you can have multiple instruments with different focal lengths. If you have a focal reducer, and you can manage this, and it's easy. You just give a name. What kind of name you want to put, Alex or
On met quoi?
Newton?
On met 300.
Oui, c'est
Comment il s'appelle? 300?
c'est 300 SL, mais Newton 300 F4, ça ira bien.
F4. Okay, then give a name. Focal length. If you have a focal reducer, it's important to provide the higher focal length, and then afterward to work with the reducer, because with the reducer, the model is trained or calculated for the focal length, but it allows to use the reducer without having another model. If you don't use the reducer and you make two different instruments with two focal lengths, you cannot use the same model and you have to buy two models. That's why it's better to use the focal reducer here. What is the focal length in millimeters?
1200.
1200.
À peu près, c'est pas.
Tu l'as exactement?
Je suis en train de chercher.
It's not critical if it's not exactly the same, but what you can do is to make a plate solve. You go on the place on the sky and take a focused image, and then plate solve it with astrometry.net or something
Je vais
like
faire
that.
avec PixInsight sur les images que tu as fait, Nico.
And the reducer is one.
It's 300.
No reduction.
What is the central obstruction? That's a percentage of the aperture of the primary mirror.
Bonne question. En pourcentage, je sais pas. Je sais qu'il fait 120 de diamètre dans le plus grand diamètre.
120?
Ouais.
C'est beaucoup. 120 mm sur 300?
Non, non, non.
C'est gros pour un Newton.
Ah, le mien fait 130. Pour 450. Pour 400.
Je crois que le grand diamètre du miroir secondaire, il fait 120, ouais. Il doit faire 90 dans le petit diamètre.
Il faut vraiment prendre la l'ombre en fait. Faut que ça c'est la taille de l'ombre en fait.
Ouais.
Bon, mais 120, non?
120. Ça...
Je suis pas sûr.
Ok. Then it's this. It's 40. It's the percentage of the diameters of the secondary against the primary. And then you have to give the pixel size in micron.
3.76.
76, yeah. And also the lambda is the bandwidth that we want to analyze. It's a good option to go to the red. That means normally we use 630, which is the middle of the red bandwidth of typical red filter. You can also go if you have H alpha or even near infrared. You can go to the red because the most you are in red, the less you have seeing problem. And then Skywave is able to manage the thing, but it's better to go. You can go to any bandwidth, but it's better to go above 600. Then normally we choose the red filter, and here it's 630. It's also able to manage the one-shot color, because now with one-shot color you can do very nice images. And then before that functionality is with the Bayer pattern and the channel we want to analyze, we had to extract manually with PixInsight the red channel, and then afterwards load it on Skywave. Now it's automatic. It loads the pattern from the fit keyword, and you can choose which channel you want to analyze. It's a 4-pixel Bayer pattern. You can choose which one you want to.
This is only for color camera?
It's only for color camera.
And with a black and white,
you don't need it.
Don't need it. Okay.
And then you have to give a rough idea of your local sync condition. On my side, I always put 1.5.
I can answer, because we didn't do any image. How many?
But it's not really critical. Then you can stay with 2.5. 2.5 is really a bad thing. Then
Yes.
normally I put 1.5.
David, on the last image we made on Trevinka, the focal length was 1198.23 millimeters in PixInsight, solved in PixInsight.
23, it's okay, then we don't need, because we cannot put after the comma. It's okay. Not really serious.
And the last one we did in when the telescope was in Syren, the focal length was 1,199. So there is a little difference.
Yeah,
there is 1 millimeter difference.
Yeah, that's not relevant.
Okay.
Now, if you have some models on the portal, you can request online. Then I will do offline request here. It works both offline and online, because I will give you a 30-day model for testing, and then I will do offline. Then we can now save the model request to a file, documents and Skywave.
And so, David, if you buy a license, the first time you do the model, you can't modify the model after license. It's okay.
No. If you buy a model, it's for a scope range. Then there is a price per scope range. That means between 8-inch and 12-inch, for example, 12 inches.
Yes.
And you can use any instrument in this range. But the model, when you request a model, it generates because there is a global model, and with this request, it specifies the model for your instrument, and it take the license you have on the portal and download the model for this instrument.
Okay.
And you can, with one model, you can have only one instrument on the model, but you can release at any time with an unlink button and activate the same model, for example, on an 8-inch for a while. There is no need to have a model for each instrument. If you have two instruments, for example, 8-inch and a 12-inch,
yes,
you can unlink and link the model when you want to use it with the same. You don't have to buy another model.
okay.
The model is needed if you have a very big difference between the size of the mirror, because we have to train the neural network model differently, because with the size it's different. We need much more iteration. It takes much more time and so on. But, that's why we have different prices for different.
Right.
And in the earlier version, we had an option to pay credit for each image analysis, but we give up this model because the people don't like it, and keep only a permanent model. When you have a model, you can use. There is no time limit. You can use.
Okay.
Then now I request the model. I will pick up the file on my premise to generate the model. And this is the file. And I will just generate now model.
And this model you requested is something that is going calculated on the fly. You don't have
Yes.
to wait for someone.
It's-
No one has to do something for it.
No one with the portal, when you do online, it's done fully automatic. We have an agent that catch your request and takes. There is a library of all different kind of mirror size and things. Also, because there is difference between refractor and reflector, we like a train ways, and we have some fork, and then we take the right model and we just put your aperture parameters to specify the model for your instrument and give back a file. That's the only thing that we have to.
Yeah, okay.
Here I will take it manually. I will enter manually because we need, we don't use the portal. And then now I generate this model. I will AIP or Alex Itik. It's better. It takes 10 seconds. And now the model is done. And then I will copy back to your premise. Let me just take this here, data, Alex. And this is the model. It's quite big because there is all the training data inside. It's 68 megabyte. And I copied back the file to you, to your PC. And the document Skywave here. Where is it? Here. Maybe with text. I don't know. It's fast. Your internet access is quite fast.
Yeah.
Because for some people it takes 10 minutes or things like this. Here it's a few seconds. That's very fast. Okay, now the model is here, and then just things that you have to do is offline load and just pick up the model. These things must be done only once. Afterward, it's saved inside the workspace, and now it's saved that you don't have to do anything. With the Pro model, you can define the reference for each optical aberration to see if your telescope is drifting. But it's really used by professional. Then with the collimator version, you don't have to use that things. Once it's done, then you can select here. If you have one, it auto select, but you might have multiple one. And then, as it's a Pro version, you have to register a token because with the Pro version, you can have multiple model at the same time, and the pricing model is different. That's why we have this token, but it's only for the Pro version. Then I will generate a token with the limitation of 30 days. Then you can use it during 30 days and or more. I don't know how much you think to evaluate the system. 30 days enough, or you need more?
I will be in Trevinca from the 1st of August until the 4th. Okay. So 30 days, it's okay, I think.
Okay. Then I will request the token, and then here, paste, 30 days, generate. But it is only for the Pro.
Okay.
Okay. Now you have 30 days. And once it's done, now you can work. Then to work, you have to connect first the system to the model you have selected here in this list, in this drop-down list. What you can do also here is to specify a folder to auto load the frame. If you check this and specify a folder, you can also give a wildcard filter to filter the frame that you want to load. For example, if you put a keyword in the file name you can type this keyword to only select the image that you want to load in Skywave. And once a new image appear, Skywave is automatically loading it, analyzing the result and showing the result on the user interface. Now we did everything. For the beginning, we don't use the autoload. We can connect, and here we are connected. And once we are connected, you can all the buttons appear. Then you can load frame, and then you can load your fit image. It's also working with other kind of image. And then you can load the image, and then it start to analyze it. Your Skywave is ready for use. If you close it and go back, we will just check if everything is okay. If I don't lose something, I think I saved everything, but we can check. Here, then you can just connect, load image. Of course, it always asks to sign it, but you can close because we don't have an account for now. And then you can just load image to work. Then now I will switch back to my computer. Then I will show you how it works with real images. And I will do a presentation of the GUI with all parts. Then you can understand how it works. This, don't that, and here it's Skywave. Okay, here I have several instruments, but it's always the same scope. But we have different focal lengths because we did some tests at factory with primary masking because we have extreme edge reflection that we have to hide. That's why I did several instruments with different models. And this model is the one we used at the factory with the guy, the Italian telescope guy on his observatory. And here of Murray, it's my Murray is my street. It's my own observatory on my premise. Then it's the same that we did on the Alex machine. That I define here the focal length, the diameter, the obstruction, pixel size, and so on. Then I will connect the instrument. And first things that we have now, we can of course load an image. We'll take one. 10.7. I did this image to manage the tilt in the 10th of July here. I load the image, and then now the system is loading the image, identifying all the suitable stars with this option, locate focus star, and choose the one which is closest to the center of the frame and analyze it automatically. It's a large frame, it's 62 megabyte sensor, a megapixel sensor, and that it takes around 30 seconds to do the analysis. And here you have the result. On this control is the collimator, and the collimators allows to. Yes.
And David, is it recommended to do it in one by one binding, or I can do this also in 2 by 2?
It's a 1 by 1.
Download times are shorter, or?
Yeah, it's not a. Yeah, of course, it depends the camera you have. If you have a ZWO, it's very fast download. The download is not a problem. I will show you why it takes sometimes so it's a bit longer, because as you can see here, that's the raw frame that is coming out from the camera, And here I define some limit. I defined a limit in radius because with my scope and with a lot of short F ratio scope, we have some problem in the when we are defocused. It makes vignetting issue, and then there is an automatically vignetted star rejection, but it's better to restrict because it's faster if you restrict the radius of the to search the stars. The advantage.
Where is
the radius, you can just play with this, then you can grow it, shrink it, or you can work with this. 42. I will keep the same radius to make 42. I want to. Okay. You can put a crosshair to see the center. Normally, to work well, I always put a star at the center because with a scope, it's better to start to align on the center and then afterward to go far from off axis, from the central axis, in order to analyze all the performance of your telescope. The advantage of this technique with AI wavefront sensing is that you can analyze any star on your frame. It's unique with this, with optomechanic devices, you cannot, it's very difficult to analyze off axis. And with this, as it's a neural network, we can crop any star anywhere, and then we can analyze the result. Then to select automatically star, we have some parameters that you can adjust. We measure on the star we have here, we measure we do a statistic on the wavefront error. And if there is very strange shape, we can reject. And we have here a sigma rejection. And by default, it's 2 or 4. I think it's 4. Here I put a large number because I wanted to analyze the tilt, and then I don't care about the shape. I just want to watch the defocus. But you can play with this to have more or less stars selected automatically. You can also work with the correlation parameters because to find the star, we make a correlation and we calculate a perfect star. It's the perfect donut we want to have. And the system is automatically comparing the perfect star with what the telescope is able to provide. And then by lowering this parameter, you can select more star. And if you want to, if you go upper, you will have less star because when the correlation threshold is not reached, it's rejected. Then you can play with this parameter, activate some rejection parameter, and then afterward locate. And it gives here the number of stars that he found on the frame.
Is there a recommendation about the star size? How big?
Yeah, you are right. That I forgot to tell that at the beginning. When I will restart, it's better. When you connect the first time without loading any frame, you get this input frame information. In here, the system is calculating for you the size in pixels of the outer ring of the donut, the external ring of the donut. And here it gives you all the parameters, the expected defocus. That means if you have a Crayford, there is 2 types of focusing. The Crayford is the best because you can go with the defocus in micron. If you are at focus and then you give the defocus from the at focus position, normally you get 99 pixel diameters in that case. But if you do the focus on the secondary mirror, as I do with this telescope, you cannot calculate because there is magnification ratio with the mirror, and then you have to go empirically. Empirically, I don't know if I spell the word correctly. And then you have to go, for example, with Nina, you have to measure the diameter, and when you get 99 pixels, you can analyze the star with this. The important is that you must stay within the tolerance. That means it's 1 millimeter point 2. It's 1,278 micron, and the tolerance is plus minus 142 microns. You have also to tell on which direction you want. The model is extrafocal, and for example, on my side, I'm intrafocal. Then if intra, it means that you push the camera sensor against the telescope, and extrafocal means that you are going out. It's after the focal point, and intra it's before the focal point. And okay, I will just switch to intrafocal.
David, the magnitude of the stars are important or not?
Yes, too bright is not good because you get saturated, and too low is not good too. Then I will show that with some star. There is an option to automatically reject the saturated star, especially if you have a field of star, as I showed before.
And open cluster is a good example. Open cluster.
For example, an open cluster with a lot of bright star but not too bright is good. One thing is also important. The system is sync tolerant, but if you use a too short exposure time, you will see moving measurement, and you will tell, oh, the system is not stable. It does not give you the same value, even if the telescope mirror doesn't. Well, we don't touch any screws, and you will see that it moves. If in reality, if you take the average of all the points, you will get the real measure. But to avoid this unexpected movement, you have to increase the integration time on your camera. That means
how much average?
It depends how fast is your telescope. On with my telescope, which is f3.342, with a red filter with magnitude 5 or something like this, I have to go between 40 and 60 seconds integration. And if you have very bright star and you have, for example, H alpha filter, you can go even more. One other thing, the system does not need guiding because the neural network learn to differentiate between astigmatism and guiding tracking error. But if there is a big tracking error, it doesn't work. You have to find a compromise between the integration time and the tracking error. But for a normal scope with a good polar alignment mount, you don't have any problem, and it works well. And yeah, then I recommend here you have a gauge or an indicator that gives you the magnitude, or not the magnitude, the ADU of the star that is selected. And if it's green, it's good. If it's above 8,000, 10,000, it's good. If it's too high, close to for example, if you have a 16-bit sampling, if it's 65,000, it becomes red. And if there is a pixel increment here, that means there is saturated pixel. It counts the saturated pixel. Then when you take an image, you have to check this bar. And if it's red, that's not good. You have to lower the integration time or select a fainter star to avoid saturation. But if you selected the reject saturated star, normally it rejects the star and not have this problem. Another things that you have to take care is the defocus error, because as you see here, we have a defocus amount and the tolerance. And this is the same here. Tolerance is here. And you can be with an error extrafocal or intrafocal. If it's minus, it's intrafocal. And you have to stay green or yellow, but not orange or red. Because if you are red, the system is not accurate enough. Then you have to stay a bit between, you have to watch this. And if it's become red, it's good. It's important to check this every time you get an image, because when you touch the screw, you are changing the focus, because you just move the forward or move the mirror, and then it defocus minus or intra or extrafocal, and sometimes you have to do some correction on the focuser to restore the right position here. And you have always to check this for each image. And also normally it's quite accurate, but sometimes correlation system does not center the star, and if the star is cropped, it doesn't work. It will give you result, but they are not accurate. The star must be completely inside the square with black margin. It must not be cropped, because otherwise the system does not provide good accurate result. But you always have everything on your screen, and then you can watch for each image that you get green, center, and then that's okay. As I said before, by default, the star that is selected is the center star, because the priority is distance from the center. Sorry, and it takes the closest star from the center. You can change this. You can choose the brightest one instead. You can change some settings, but by default it's like this. And here you have a list of all stars that was detected on the frame, with some information: the position on the sensor, the flux, the ADU, the distance from the radius, the correlation amount, that means the correlation between the perfect star for your telescope and what you found on the
and you can see each image of star. If you
yes,
want.
you can analyze each star differently. You can just pick up here, or if you want to go on the sensor itself, you can just pick up a star with a shift click and click inside the box here, and the system will take another star to analyze it. And then you will see, of course, the measurement of that star directly. Here you can see that as I have tilt, the defocus error increase, because the tilt is changing the focus. Then the defocus increased, now it's yellow, and but the comma is quite stable, a bit less. Astigmatism is not good here. And we have also the position of the star from the middle of the sensor, minus 195 pixels and minus 1300. And you can see here the green one. The green one is the one that is actually analyzed. And you can also crop more star. There is a manual crop. If you want to take that one, for example, you can just center it and crop it to add additional star. But as it was rejected, I think it's Finder star or something like this. But you can manually crop to add on the list additional star. But normally when you are doing alignment, you don't need to do that. And for special things that you can do it manually. And now it will analyze this star. And then you can see the result here. The focus is quite good. Here it's very faint. That's why there is a hot pixel here. That's why we can't see it well. If I go, this is the star that is displayed in the square here. But here there is an auto stretch. That's why you can see like this. here the signal is really bad. If you look at this, there is 1,800 ADU. It's not enough. It's not good to select such star to analyze because there is not enough signal to do a proper analysis. I will go back now to the center star. Shift click, and then you just click on inside and select, or you can go on the list here. You can add star, save, delete a star with the buttons here. When the boxes are checked, it does the cascade automatically the things. For each new image, it locate and take the closest and analyze it directly. If you uncheck this, you have to click the button manually. If you are not allowed, you must check all those things, then you don't have to do anything. The system will take the star. If you even if it moves on the sensor, because when you are turning the knobs, sometimes there is wandering of the star because when you change the tilt, it moves across. But as it selects always the star that is close to the center, in that case, normally it always reselect automatically the right one. Of course, if there is two bright stars together, sometimes it can flip between each other. But as the stars are close to the center, it doesn't matter. You can even work.
And it works.
It works, yes.
Okay.
It works. Yeah, it works. Okay, then now we have the star analyzed. Then I will go to the different display we have here. We have, we can see, of course, the raw frame with all stars selected. We can see the one that is selected now with a 3D view. You can see how it looks. Typically, when you have comma, you can have 0 comma with offsetted shade, offset central obstruction. The central obstruction is not, the center of the central obstruction is not a good indicator of no comma. The comma is visible with a slope in the flux. If there is a big slope, that means that there is a comma. But the central obstruction may be offsetted. It's not a good indicator. It's because when the shadow is cast on the sensor, the shadow is not cast by the mirror, but by the baffle. And the baffle are almost never correctly aligned. And if you take the baffle as a reference, you will decollimate your telescope. It's never a good idea. You can make a rough alignment with this, but it's not, even if it's perfectly aligned with no offset, it's not a good thing. The good indicator is to check in 3D. And if your plot is very flat, like is it here, that means there is no comma. If there is a slope, that means there is comma. It's better to check that. Then the defocus star is the selected one. You can go and analyze also the pixel per pixel, what is the value, ADU, and so on. The system is also able to reconstruct the PSF. It's the PSF, here we have a lot of astigmatism, that's why we see that. And on the middle, we can see the airy disk. That means normally, if you have a very good instrument perfectly aligned at diffraction limit, all the signal is inside this airy disk. That means here we lose performance because we have this typical shape of the astigmatism, and it's outside the airy disk. Of course, you have also the 3D view of this, but it's not very useful in 3D, but there is the option 3D view. You can see also square root PSF. It makes much more visibility of the rings, the ripples. And you can also see the seeing limited. That means it's the how a star will look like with a specific seeing here, 1.5 with this telescope performance. And with this slider, you can go between the diffraction limit star, which is very round circular, and your telescope. This is the astigmatism shape. Those things are available on the collimator version. You can see the PSF. One thing is specific to this version is the wavefront. This is not available with the collimator version because the wavefront is for optical engineer. It shows the shape of your mirror with the peak in red and the valley here. And you can display the performance, the Strel ratio. Here is very low. The Strel ratio is low because it's not well collimated. And the system is able to give you the Strel ratio. We don't give that because the manufacturer of telescope don't like that we communicate the Strel ratio because it's really sensitive indicator. And sometimes people, because they sell telescope with diffraction limit performances, and if you don't have a very well collimated telescope with a good sky, it's difficult to reach the diffraction limit. That's why they don't like this, because they are challenged by their customer. That's why we don't give that to amateur people. We also have a 3D view of this wavefront. You can see how with here it's a wave, error wave. And we can see here how your mirror, like it looks distorted because the scale is very small. In reality, it's flat, but as we have an auto scale system, it just makes this shape.
David, when you use the raw image before, I've seen how to say 9.4 or 9.2 depends on which star you have chosen. And you say that the telescope is not in good collimation. So this
the telescope, the comma is good, but we have the same error as Alexander and Nicolas have. We have astigmatism because the corrector optical axis is not well aligned with the primary and secondary mirror. That's why we have. I will show you the same telescope with the diffraction limit performance where everything is aligned. There is still a tilt problem, but the telescope is perfectly collimated. I will show you this later. The second thing is the MTF, is the performance of your telescope. In green here, you see your telescope with at diffraction limit. It's the perfect instrument. And the red is this instrument with the current aberration. And of course, you can push this by collimating. You can go close to this line. The closer you are, the best image you get after. And you have also this. It's the encircled energy. It's the energy inside the airy disk. Same things, that it's the scope at with the current performance, and it's the optimal curve. But the main things for aligning is this, only this control. These are for to see the performance with some plots, but it's only with the Pro. With the collimator version, you only have this, and PSF, and you don't have it. The last thing that is really important is the field aberration. Typically with low F number, below 4 also, sensor tilts become very relevant. And if you have a tilt like I have here, I have 4 times the critical focus zone. It's really big. We can see a real defocus between the center star and the star at close to the border of the sensor. And we can see the error here with the direction of the error. That means there is a tilt here. it's 150 micron tilt on the y-axis, and -5, it's almost centered, but it's a tilt on the y-axis. Then I have to act on the screw to correct with a sensor tilt correction to correct the tilt here. And to do that tilt analysis, only one star is not enough. That's why here we use all stars that are available, and we measure the defocus error of each star to calculate the angle of the tilt. And with this option, we can use we can manage the tilt, and then you know which screw you have to turn to fix to correct the tilt. And of course, you can align the screw with the tilt corrector screw by changing the angle.
David, if I understand, you can separate the tilt from the astigmatism of the secondary mirror.
Exactly. One very important thing, as it's a sensor, it's a curvature sensor, means that it analyzes the peak and the valley of your mirror.
Yes.
That means he can separate each aberration. You can see them here. You have here the spherical aberration. You have here the astigmatism, the coma, and the trefoil. And the tilt is not all these things. Tilt only act on the defocus, meaning that if you are perfectly focused at the center and you go on the top of the frame, you will have a defocus star. And for example, if we measure the full width half maximum, like Nina do, you can see the difference. The value will not be the same because of this defocus. But in that case, it does not use the full width as its derivative approach. It really measures the defocus on your camera. That's why it's able to show you the defocus on this target. And another thing which is also using the field analysis is the astigmatism, because when you are normally, you can manage the astigmatism that must be close to 0 on the center of your scope. But as far as you go off axis, you will get some astigmatism because you cannot correct the full. It's difficult to have a fully corrected optics. Then sometimes you cannot have no astigmatism everywhere on the frame. On the center, it's okay, but when you go off axis, the astigmatism will go up. And then the very important thing is to balance the astigmatism. That thinks that at the center, if you are close to 0, it will never be to 0, but close to 0. If you go, I don't know, 1000 pixels on that direction, you will measure an astigmatism which is not 0, it's increasing. As far as you go off axis, it's increasing. And if you go on the opposite way, you should have almost the same value. But it's not easy to get it, because if you work only on the center, you will see only the center star and the astigmatism value of the center star, and you will see how it's close to 0, it's okay. But it can be close to 0 center, but not balanced. That means on the corner of the shape, you will have a strong astigmatism. On the middle, it's okay, and on the other corner, it's also strong, but not the same value. With this, you can make a balance of your astigmatism to have the best that you can reach with your instrument. That's why we put this option, and it measures here the angle, the direction of the astigmatism, and it measures the amount of the astigmatism. Here we are quite well. The best will, of course, will be in the red circle, but it's about 90%. It's okay. We can live with that. And all those apparitions can be seen also with the star distribution here. We have different value that we can, different path that we can. Here we see the curvature. We see the tilt here because the center, the real center of the telescope is here. It must be normally at the center. We can see some things like this. Then normally, as I said before, you can work only with this control. Then the first thing that must be done is go to the center star and minimize the comma. That means normally to minimize the comma, we work on the primary. That means we select the mirror one. We select how many screws. Normally it's 3, but it can be 4 on some telescope. And then you have to align the screw with this control to be accurate with your telescope. And to do that alignment of the screw with your scope, you must stand by the telescope. And then there is a procedure that I can show. You have it here. A procedure. I think it's in here. You have a procedure here to align that. This is the target, and it's like where you are looking inside the telescope. Your eye are going in front of the telescope to the primary mirror. And then you have to align the screw with the screw on the primary and on the secondary. And at the end, if you have a tilt, to the tilt correction plate. And there is a procedure which is described here. The procedure is quite easy. You have to detect the sensor, the orientation. Normally, on the rectangle sensor, the longest length is X and the shortest is Y. But it can be like it's landscape position. It can be also portrait. And you have to identify that in the raw image. If it's not correct, you can flip the axis here to get the right one. And this is very important to know which screw you have to turn, because if you have the astigmatism here, if the screws are well aligned, you know that you have to go, for example, on the secondary mirror, release that one and tighten those one. To push slightly with very small movement, to push the error, to reduce the error in order to get to reach the center of the target. This is why it's the axis alignment, screw alignment is a very, very important process. You can go empirically, but sometimes you will lose a lot of time because you are going in the wrong direction. It's better to do this procedure. It's a bit cumbersome the first time, but once it's done, you don't have to do it anymore. And then,
David?
yeah.
Excuse me. Our telescope has only 3 spider veins. Is it a problem or?
No, there is no problem.
Okay.
You can have different spider are to train the neural network. We use a very different shape of spider.
Okay.
To be sure that the neural network is able to ignore them. But it's not important, the number of spiders. The things that is very important is that the central obstruction is circular. If you have, for example, like a hyperstar with a filter wheel that makes not a round shape, it's a really problem. Normally, I have a friend who have this problem. I just print with a 3D print a mask to restore a circular aperture, circular central obstruction.
Okay.
We can, of course, train model with different shape, but it's really rare, and it takes time to do that.
Okay.
That's why we kept.
What I meant was the shadow of the spider does not have to be aligned with X and Y.
No. The system knows to eliminate that. It does not care about the spider.
Okay.
To define the correct axis, you have to put your finger when you take a frame, your hand or finger at the front of the telescope on the position. If, for example, if you see the sensor here, and you want to check that the plus X axis is correctly aligned, if you go to the front, you can put your hand to that side, take a picture, and you can see on the image if there is a shadow on the right direction. If you put on the X plus X, you will see the shadow here. You know that the X that you see here is correctly aligned with the telescope. If it's not the case, you can just flip the axis by just clicking those checkbox. Then you can do that for the X and check if, yeah, for example, we can see here, we put a label to know that the plus X is on top here. Normally it should be on the side, but here it's on top, depending the position of the camera. And then you label the plus X on top and then plus Y, sorry. And you can label the plus Y and with two end placed on top of the telescope, and then you can just align your axis with this. And once its axis it's aligned, you can align the screw. You can check where the screw are and then give the correct position and label the screw. Normally, you should always label it as you see inside the scope. That means you are in front of your scope and you see inside the scope. That means the screw one is here on top, in that case. Oh, I will just zoom. One is here, two is on Y, and three on the other. And then you have to label your screw and label your axis before starting to do alignment. You can do it without doing this procedure, but you will lose time because sometimes you don't know which screw you have to turn, and you will lose time and make decollimation instead of collimation. It's really important, I think. I go back now. Once your screw are aligned, your sensor is correctly placed, and everything is aligned, then you can start. And every time you load an image, it goes to the collimator automatically, show you the result. First, start with the comma, fix the comma.
So first, David, please, you correge the primary with this.
The first for the comma on the Newton, the comma is the primary. Yeah? You can just reduce the comma with just clicking this and looks how it goes. If the comma is here, you have to tighten the 1, release the 2 and 3, and then push step by step the error, reduce the error. You will have a scatter plot here. You can review the previous analysis on the target, like a gunshot on the target. You can just put your and look the result. And normally, if you go in the right direction, you can see it very quickly.
Okay. And
once the comma is done, is fixed, you can go to astigmatism. It's the same, but for you, in your case, the astigmatism is a problem with the secondary mirror. And then you have to go to the secondary mirror. Of course, the secondary mirror, you have to go to secondary, and also the screw of the secondary must have been aligned first to be sure that you are always going on the same way. And in that case, that means you have to tighten the 2 and release the 1 and 3, and then to push here. Of course, this is at the center of the sensor. Normally, you should be able to manage the error to be close to or inside the green. That means value here above 9 or plus. The center is 10. I can show you the problem on your scope. I prepare a very small schema. Here you have the typical Newtonian scheme. The red is the corrector. And when here is the 45-degree mirror, and it can be a tilt tip on 2 directions. It can be X and Y. And if it's X and Y, it's not the center of the, see the purple is the pupil of the telescope reflected by the primary to the sensor. When it's aligned, the center of the cone is aligned with the center of the corrector. But if there is a tilt tip X and Y, it's not center. It's tilted. The light ray are tilted and goes across the lens. You can see here, it goes across the lens, not centered. That's why you have astigmatism. If it's well centered, you can see a perfect symmetry on both, and here it's distorted. That's why you get astigmatism. And then what you have to do is to minimize the astigmatism by just tightening the screws in order to reduce the astigmatism. And that means you push the center of the cone towards the center of the corrector. This is a typical problem with comma corrector. For example, at Chile, I don't remember the name of the farm, Obstec, sorry, at Obstec, they have a lot of epsilon, and epsilon it's like a Newton, but it's not circular. No, it's not circular. It's not.
It's a different kind of main mirror.
Exactly. Sorry, it's hyperbolic. It's not circular.
Spherical?
It's not spherical. Sorry, well, it's not spherical. It's hyperbolic. But there is also a corrector, and there is a lot of problem with the corrector because it's bolted inside, and they have to put some shime in order to fix the X and Y offset and the problem that they have with this corrector. And even if it's fixed, the telescope is at diffraction limit. But it's a common problem with the Newtonian or with telescope like mine, because it's also there is also a wine corrector with lenses. If it's not centered, you have this. If it's an offset like this, it's not really a problem because it's a less. But if the beam is tilted, it's really a big problem. That's I think you have, because here as it's a three screw correction, you are never offsetted. You are always tilted. That means it goes diagonally across the corrector. Then if you go back here, once you are on the secondary, that means you ignore totally the primary. You are only on the secondary, and then you turn the knob in order to center the astigmatism. Once your astigmatism is good, that means the bar is not red anymore. It can be yellow or green. And that meaning that you are at the center, you are aligned. Even if you are aligned at the center, it doesn't mean that you are perfectly balanced between across both sides of the sensor. Meaning that if you have here no astigmatism or almost very few astigmatism, if you go here and measure and go here and measure, maybe you will have different astigmatism value, meaning that it's not balanced. And with this, as star field with and disruption, it will allow you to center the astigmatism, and then you can continue to manage the screw in order to push this target in the center of the cursor in the center of the target in order to be balanced. Because in terms of imaging, it's better to be balanced across the full field in order to have the same star shape across the whole field, instead of having a perfect centered star and bad shape in the side.
David, for me, that I get the things right, as I understand, we start at the primary mirror with the middle star in the middle because of the coma. But when we see that there is astigmatism, we have to fine-tune this at the secondary.
Exactly.
For the cone error. But normally when I change the secondary, I have to redo the fine tuning on the primary.
Yeah, it happens. Even normally when you converge, there is you don't have to move a lot, but if there is a big error, you have to make some iteration between astigmatism on the secondary, comma, and then you can iterate slowly to recenter, of course, because when you change, maybe you will add comma, and you have to find slightly the right alignment of your two axes.
Okay,
And
thank you.
you can iterate even in the same image, and then you can go astigmatism, make an iteration, it goes on the right direction, then okay, you see okay, then now you take a new image, you see that's okay, and then you go to comma, and okay, comma, okay, it's a little bit worse, but it's still acceptable. Then you can go further, and so on. If you have to do adjustment, you can go to the primary, adjust a bit, and so on, going slowly to reach the convergence between the.
And I have to switch between coma and astigmatism and the mirrors also, right? I have
exactly.
to
This is the
switch
primary.
between mirror 1 and 2.
Yeah, mirror, exactly. Mirror 1 for the comma. It's not automatic because it depends the kind of telescope. Then you have to take care about that. Then switching here. You can also hide the screw if you don't want it.
And on the same image, you can do the comma and astigmatism just after.
Just by selecting the aberration. Because all the, here it's on the Pro, these things that you can see the value of each aberration there. It's the beauty of the Zernical decomposition that it's a way to separate, or method to separate each aberration on a different mathematical term. And then if you change the comma, it does not have influence of the astigmatism. Then you can work on each aberration separately without taking care. Because if you don't have this separation with the indirect method, everything is mixed together and you never know what you are doing. With this, you can see very accurately what you are doing. And that's why we have this selector in the target here to select the right aberration. At the end, if you want to see the global score, you can just activate all the aberration and then the system will give you the performance, overall performance of your scope. Here it's not very bad, but it's not perfect, especially for such scope. We can go further. Then, but you never change the screw with all those selected because it mixes up together and then it does not give you a clear result. You have to go very one by one and switch the mirror and so on. Another thing that is quite important, not with Newtonian, but with other like a Cassegrain, it's the spherical aberration. The spherical aberration in that case measure the distance between the two mirrors. And if you have a bad distance, it generates aberration. And spherical aberration is like a defocus error. It makes a bloated star. I will just turn on the light, sorry. It makes a bloated star, and you lose performance if you have a strong spherical error. And the last error is the trefoil. It's also important for Newtonian. For example, if you tighten too much the push-pull screws, you will generate a stress on the optical things on the mirror, and then you will have the trefoil that is growing. That means that your mirror is on tension, and it generated. We call that trefoil. It's like it makes.
This is on the secondary or on the primary?
On here, it's on the. You cannot differentiate because you see you see the primary and the secondary. But with the Newtonian, it's very rarely on the secondary. It's mainly on the primary because the secondary is just a reflector. It's very rare that there is tension on the secondary. But with Ritchie-Chrétien or with the Cassegrain style telescope, there is very often some stress on the mirror because it's too tightened. And if you have push-pull, maybe sometimes the two are on tension and it makes a deformation on the mirror. And then you can see that in that with that indicator. And here I don't have any trefoil, but as you told me, Nicolas, you have some trefoil on one of your scope. And maybe it's because there is a tension somewhere. The difficult things is to identify where is it. Because you don't need a lot to see a tension. It can be something very very small tension that is enough to make a deformation on the mirror. Okay, then I will make just a summary of all what we see here. We have a lot of indicator to display the tilt and things. We also have here the aberration. Here you can see there is a lot of astigmatism. Now I will show you an image where is the telescope at when it goes out from the factory, because it was uncollimated during the transport, not a lot, but enough to be bad. It was this. Let's check. 22, 38, 12. This one. I switched the model because there was some difference in the obstruction and there was no baffle and things like this that were not yet mounted. That's why I have a different model.
Repeat, David, the time exposure, it's 40 seconds?
Here it's, yeah, it's between, I always stick on between 30 seconds and 60 seconds to get...
without guiding.
Exactly.
You do without guiding.
I have a 10 micron that I don't need guiding even for 10 minutes, but even with not a 10 micron, with how you call that? On the 10 micron, you have, I'm searching the word, you have encoder that auto-correct the mechanical error, but even without that, there is no need to guide. Of course, if you go 5 minutes, you will need to guide, but for 30 seconds, there is no...
They correct following the encoder and not the... Yeah, that's it.
Yeah. Here it's an image.
Paramount, maybe they have encoder. They could add encoder if we had it. And it's an option. It's a basic.
But it's not mandatory. Without encoder with a proper T point, there is no need to encoder. But of course, encoder is really the best. You don't have to do anything. It makes the PEC automatically. It makes all the things automatically. You can even release the clutch and turn the things, and it always knows or where is it. You don't have to re-index the things. And it's really good, but with a 10 micron, you have to guide when the thing is below 1 arc seconds, because with long focal, sometimes you get better result, but it's really good. Here it's an image that we grab in May with the engineer, Italian telescope engineer on his facility. And then you can see we have very good performance. We are close to 0.05 wave error on. Also, astigmatism is very good. It's close to the center axis. And if I measure the Strel, here it's quite good, 82. And if I pick up another star, because it's not, the tilt is not perfect here. If I pick up this star, I will go higher than 92% Strel. It's a perfect telescope. Now, above 80%, you are limited by the sky. Sky on Earth can limit the scope. The scope, the sky is the limit in that case. Yeah, you see, you have really very good result. No spherical, almost no trefoil. You can see here 0.1, 0.3, and those indicators higher order spherical means if there is polishing problem on the mirror, you can see it here. For example, if you have turned on edge reflection on the far edge, you can see that here. But it's for optician. This is not. Then here the telescope is perfect, and if I go here, I can see that in 92 Strel ratio, and we have 0.05 wave error between the peak and valley. It's really flat. It's perfect telescope. If you can reach that, you will be very happy, I think. 80% is already a good point, but 92 we can. And if you look now at the PSF, for example, that's the PSF. You can see it's perfect. It's inside the Iridis.
They take the image out of the factory?
Yeah. In fact, we spent several nights on the observatory of Leonardo. Leonardo is the owner and the engineer of the main engineer of the company, Telescope Italian Telescope. And we found a lot of, he was amazed because we do some tests on both sides of the meridian on 90 degree, 20 degree, close to the horizon, and to check if it moves. And I told him it moves. He said it's impossible. Our mechanical parts are very strong, very well designed. It cannot move. And see it move. I can show you. And he said, oh, it's Skywave. It's not accurate. I said, no, I can show you that if I go back to the original position of the sky, same altitude, I get exactly the same value. And he agreed, and he did a full check, rechecking all screws of the truss tub, and he found that there was some loosened screw that makes a slight movement between the both sides of the meridian. Then it's really accurate. Just to give you an idea, not me, but Gaston Boda, the inventor of the things, the guy who did the model and things like this. He's working with professional organization like ESO, ESA, Airbus, and so on, in order to make adaptive optic, which is able to measure 1,000 times per second. It's millisecond measurement with GPU in order to control piezo mirror to correct the sky, the turbulence of the sky. And the method is really, really accurate. And of course, for amateur, it's not so far, but the methodology is the same. There is no difference. Just the model is trained differently. And now if we go to the performance of the telescope, you can see the green line is the perfect telescope, and the red is the one we have now. We are close to the perfection. And yeah, you can see here it's what you see on the sky with 1 arc-second seeing. And if you go now to the both side diffraction limit, you can see almost no difference. Just a little bit, but it's not noticeable. It's really, really few.
So Alex, that's your goal for the next day. So
yeah, for Alex, just to make a small review of what we did there, because there was a lot of things. Then first thing that you have to be sure that you get a good defocus. That means you have to, if you have absolute focuser, you can focus your telescope and then go extra focal by this value, 1,000. No, not this one, but the one which is displayed on yours. I can show you that now. Sorry, I made a mistake. It's this. When I connect, it's connected. You must go 1,493 microns, and then you can capture the image in Nina. I don't know which sequencer you use, but
yeah,
if it's
Nina.
Nina, perfect. And then you can measure with Nina on the frame. You can right-click, check X and Y, and if you get almost this value, 125 pixel diameter, you are good. You can load it. Normally, it works like this. If it's at the focus, when you defocus, you should get this value. With the Crayford, it's always working. With focuser on the secondary, sometimes you have to search empirically, because it gives you a defocus icon, but it's never correct because there is magnification between the mirror, because the mirror are not flat. They are changing the power, and it makes a different value. In that case, on my telescope, I always go to Nina and measure both sides. And when I'm close to 100 and I'm okay, then I load the image and it works.
So sorry, David. When I defocus,
yeah,
it has to be 1,493 microns.
Micron from the focal point. That means you make the perfect, the best focus you can reach. And then once you are at the focus, you do the defocus extrafocal by this amount.
Okay.
You add this. Yeah.
Considering with the Atlas, which has 80 nanometers per step, it makes well, I have to calculate the. Okay.
You have to convert the step because the steps is not the micron. Some focuser that you can enter the micron, it makes the calculation for you. Otherwise, you have to do this operation by yourself. And the best, even if you do that like this, the best is to double check with the diameter. If it's 128 or 124, 3, it doesn't matter. You can even load it.
Step. So, okay, so it makes okay, 18,000 almost steps. Okay, and so when you say extrafocal, it's when I move the focuser in, so the focus.
No, out. That means the camera is going out. When you intrafocal is going through the telescope, toward the telescope, and extrafocal is.
I always thought that intrafocal is when if you have the focal plane, your intrafocal is, and the outside of the telescope is here. Intrafocal is here.
Yeah.
So the camera is outside, is going out. And extrafocal, you are out, you are far from the focal plane, so the camera is in. You have to move out to go to extrafocal.
Exactly. It's not well. I will just.
So when I want to defocus extrafocally, I have to move the camera in.
No,
out. No, Alex. It is you have to go far.
I will show you that.
Si je m'éloigne.
Si tu t'éloignes, tu viens.
Extrafocal.
Voilà. Ici, si tu es sur le point focal,
ouais.
Tu recules la caméra.
Tu es au point de convergence ici.
Ouais.
Si tu avances, tu viens contre là, c'est le télescope, tu as la sortie. Ouais. Si tu avances, tu es intrafocal.
Et non, tu es extrafocal.
Non, extra, c'est là. Intra, tu rentres à l'intérieur. Et extra, tu sors.
Ouais, d'accord. Okay.
Bon,
tu éloignes la caméra.
In reality, the intra or extra does not matter. It's just the some aberration will change the sign. That sometimes it's not good for the screw. That's why it's important to have a good focal intra or extra focal choice, because otherwise the screw are not acting correctly. On my case, I'm intrafocal, but the value does not change, just the sign are changing. Because in reality, if you are on both sides of the focal point, the shape is the same. The shape of the star is the same. It should be. If your telescope is good, if you have a big spherical aberration, it's not. It will be different. But if you have a good telescope, there is almost no differences.
Okay.
Donc, tu sors la caméra, c'est extra. Tu rentres la caméra, c'est intra.
Ok.
Tu tournes le créford à l'intérieur, c'est intra. Tu sors le focuseur, c'est extra.
Ok.
When you tell empirically, that mean step by step, iteratively, or how you obtain your value, your empirical value?
Okay, then we start first with the comma, as I did before, as
Yeah.
I said before. We go to the center and we minimize the comma. And then afterwards, we saw that we had astigmatism. And we think about how it can be. We check the mechanical part because, and Leonardo, the engineer, take back the telescope from to the lab, and with a very accurate caliper, it just checked the position of the corrector. He said there is very few offset. It's sent. It's around 10 microns error. It's really few, and it does not. It's not a mechanical problem. And I told him he did a laser alignment because the Italian telescope, they have a place to put a laser inside for collimation. And he said it was perfectly laser aligned, but it's of course laser aligned, but it's not accurate enough. The best thing is to do it on the sky with a real measurement of the wavefront. And in fact, the position of the center was offsetted. And as you can see here, even after that, it was not centered. The perfect position is here. It's 376 pixels from the optical center. It's really good. You can stand with this result because it's enough to make superb image. But if you want to be better, you can just change the position of the secondary to put that point here to get a perfect result at the center. And then if I go back to the procedure, first we did the comma, and then with the comma we saw that there was movement. Then we checked some position on the sky, and the direction of the comma changed. Not very far. At the beginning, it was far because there was a problem with the primary. It was not there. There was one point on the primary that was not touching the mirror, and there was an offset. And he checked that and corrected that. And the second problem was on the thrust tub. The thrust tub was not tightened enough, and we saw still a movement. And once the comma was perfectly not moving on both sides of the meridian at different altitude, we know that the telescope was strong and mechanical issue was stabilized. And then we still had an astigmatism. And then as we had strong tilt, we found that the optical center, because when you tilt the plate, the optical center is not centered on the center of your sensor, because with the tilt, the center is moving. Then we manage the tilt, and we get a result with a good value, but not here, somewhere here or very quite far off the center. And then we just afterward the secondary mirror to put this here. We stop at this point because it was late on the night. We spent several nights consecutively, and we were very tired. And then we stopped because the problem was the tilt. And as the tilt corrector was not good because it's the zero tilt, it's mounted on the camera, and we had always to unscrew the camera with the caliper of the push-pull, rescrew the camera, take an image. Of course, there is other movement, and we lose a lot of time. And I decided to change the tilt corrector with something better mechanically. And then I told him that we can stop here because the telescope is perfect. We cannot go further with the telescope. The problem is the tilt now, especially at f3.4. The tilt is really a problem because you can have a big defocus here. We have a defocus error of minus 20 micron. If I go in that place, you can see that the value will go up now. And it's enough to make a bloated star on the corner. It's important with this fast telescope to manage correctly the tilt. Oh, I know it's.
And David, when you do this iteration between primary, secondary, and you do another image, you do primary, secondary, and after that you can analyze the field.
Yeah.
On the second check step.
Yeah.
And you change only the secondary for astigmatism on the field.
Yes. Okay. I will. I know what error I did. It's tilted X. That's why if I choose on the X on the same side, you will see no. If I go here, for example, you will see that the defocus error is. I will go again a full step to explain how you can proceed. First is to check the The first thing that is important to do is not to turn nothing. Oh, it's always this. I think it's really strange. Or still two. I will pick up this one. Important is before turning any knobs is checking the result. That means you take a star, not too brighter. Here in that case, I use 21 Cygni, which is on the Cygnus constellation, and it's there is a lot of star, and then you have enough to work, and then it's also it's close to the zenith. It's good because there is less atmosphere, and here you can see the defocus error increase because it's tilted on XY on the x-axis, not on the y-axis, and it's enough to have a bloated star on the corner of the sensor. If I repeat, then first you can take several measures of the same star field and check if the results are consistent. That means you have a good capture time, enough to manage the seeing, and all the measurements must be close together. The point, it will move, of course, because it's not. There is some variation due to the seeing, to the turbulence also on your observatory. If you move beside the telescope, it must move, but it must be very slight movement. And once it's stable, you know that you have a good measurement, and you can start with turning the knobs. First, you go with the comma and turn the primary knob in order to solve the comma. If the comma is good enough, you don't have to do that, and you can go directly to the astigmatism. And then now you move in front of the telescope to turn the secondary knob in order to
on the same image, on the same image, or
on the same image. If you, for example, take an image, analyze it, yes. You see, oh, my comma is good. Okay. My comma is good, is here. If you said it's good. Okay, then now I want to see if the astigmatism is good. Then you, without loading a new image, you can check this, and then here it's good. But if it's here, you say, oh, I have to correct the astigmatism. Then you go in front of your mirror. You make a small adjustment of the scope, very small, just a 20th of the, or 20, I don't know, a 15 of a full turn, or just a slight movement on the screw. Take a new image and check how it behaves. And with this, you can see with a very small movement if it's going well. Sometimes it's not enough to do one movement to see the real direction because there is some tension in the mechanical tension. Then sometimes you have to go with 2-3 images to check to find the correct direction. And if you move one step astigmatism in the right direction, you can, I want to see if my comma is still good, then you can go here on the same image without reloading. It will give you the value of the comma. If it's still good, of course, it will always move a bit. It's normal. But if it's still inside close to 9 or more, you can say, okay, it's enough. You also have to check if the defocus is still good. And then you can continue with astigmatism. Now, if your comma is bad, then you can go back to the primary, turn the knob of your primary, load the image. Oh, it's better. Now it's now good. And go back without reloading to astigmatism. Okay, it's worse or it's better. And if it's worse, you can just move a slide to wander around the optical center. And then you will find it will never be perfect. It's almost impossible because, but it will close to the perfection.
If you are on the red, it is good.
Yes.
If you are on the green, it is okay. If
you're on the green, it's okay. Yeah.
Okay.
When the score is above is above 9, even 8.9, it's enough. Here, if I make a cumul of all aberration, you see at 8.6, 8.6 is 92 of Strel ratio. It's perfect, and it's the cumul of all aberration. If I take only the comma, I have 8.9. I can still work on this because with the TI telescope, it's really easy to manage the comma because they don't have push-pull. They have a screw with pre-constrained un ressort, je sais plus comment on dit, spring. And then you can just adjust very slightly, and it's easy to push to more than 9. Then you can still play around this, but at some points you have to stop because otherwise you become crazy because you will manage fraction of wave. It does not matter because at this point you are limited by the sky. Even if the sky is below 1 arc second of seeing, then you will see no difference. That you have to.
The field analysis, it is after.
Yeah, once your telescope is here, if you can reach it, you can go to field analysis. You can see here my sensor is not good because there is 4 times the critical focus zone. That means here if I see the tilt here it's the peak, and here it's the valley. You see here is the center of the image, and it's not good because here there is a strong defocus on the extrafocal, and here it's a strong defocus intrafocal, which is the same, and the result is the same. If you measure, if it's balanced, if you measure the FWHM, you will get the same value, and here it's perfectly focused. And that's a big problem with F number lower than 4. You have a strong defocus, and it's visible on the image. Then you have to fix the tilt. But when you fix the tilt, it's only moving the screw of the tilt correction. There is nothing on the mirror. The telescope is still at diffraction limit. You will never change this by when you change the tilt correctors. 2 things different. And the latest thing that you can do, if it's perfectly tilt and it says okay, you can finish with astigmatism balance. That means you will balance the astigmatism amount. Here is the middle of the sensor. If the astigmatism is good at the middle of the sensor, it must be balanced on the whole sensor. And you can fix that also with this measurement analysis. And then in that case, you can still correct with the secondary mirror screws in order to move a bit. Even if it goes a bit worse on the center, sometimes it's better to be balanced instead of having a perfect star at the center, but a unbalanced result across the field. Because if it's a lot, you will see some astigmatism on the corner and on the center it's good. Sometimes some people crop the frame to remove the bad astigmatism on the corner. But it's better to balance this, then you can have a balanced result at the end. And
but with this, David, you do a new iteration between the secondary and
yes,
primary, but
no,
very small correction.
yes, maybe you still have to adjust a comma if it's going bad, but if you are already close to the center, normally there is very slight, but you don't have to go too much. But you can still go with the same frame, you can still remeasure or redisplay the comma, and if you see some movement, you must converge close to the perfect result slightly. At the end, there is almost no move, very slight movement, just 20th of the
20e de tour, ouais.
20e de tour.
David, I don't have a tilter unit in my image train. So the last thing you said, I think maybe that could be a case because I can't correct the tilt there. It's better to do this, compensate this with over the field analysis with secondary then a little bit.
Yeah, exactly. No, not for the tilt. For the astigmatism, you have to go to the telescope because astigmatism is nothing with the sensor tilt. It's really a measure of the value of astigmatism across the field.
Yes.
That means we just take each star that we can see here, and we measure the astigmatism, oblique and vertical astigmatism here, each value of each star. And then we check if the value on that side and that side and that side are the same. The value will be balanced if you go here with no astigmatism. If you are, I don't know, 1000 pixels somewhere here, and if you make a circle, it must be the same value. That means it's balanced on all sides at a constant radius across the center. The astigmatism remain the same. And then it's important because if you are not aligned, maybe the astigmatism on that side of the sensor is very good, and here it's very bad. It happens often. If you look at amateur image, you will see, if you look closely, sometimes the star shape are very good on one side and very the shape is distorted because of the astigmatism on the other side.
Yeah.
And this is because it's not balanced. At the center, it could be quite good, but off axis, if it's unbalanced, you will see different results. And the best is to have something balanced. Depending of your optical, mechanical things, optical performance, type of corrector, you cannot have a full field perfectly corrected. You still have some astigmatism, but you can balance it to have a very nice result and balanced result across the full field. That's why it's important. But it's not mandatory if you don't want to do that, because here you are happy with the result you get, you can stop. And when you get a result that you can say, oh, it's not bad, the good thing is to do a test on the star at focus and analyze the full width alpha maximum with Nina, for example, check if it looks good, and you can zoom on your raw frame in order to check the result, to have a good feedback. And if you are happy with this, you can stop, because sometimes trying to go better is going worse. Then sometimes it's good to say, okay, at this stage I stop here. I will take some time to You don't have to rush. You can go slowly and do one step, check that the result on the sky with real image, focused image. And if you are happy with the result, you can stop. It's not mandatory to go on this. Even with this error, it's okay, it's red, but you can check on the image. Maybe you see that I don't see any difference because the seeing is masking this error. Sometimes it happens that the thing is that the average thing you have on your observatory place, it just blow up the things, and then you cannot see any difference. Even if you center this, you will not see difference on the image because the thing is blurring the shape. If I increase the thing here, so I put 4, for example, it will recalculate the things, then you can see what will happen. And you see the thing is doing that. It's just blurring the things. And if you go to very accurately and then the thing is just inside this, you will see nothing. That it does not make sense to go further with the alignment. That's why it's good idea to go to make some step and check and see what the result, if it's looking good on the whole frame. And if you are not happy and you still see some bad things, you can continue. Then doing iteratively some tests. I do that. I do that because I don't want to be perfect. You can never be perfect. And also with different temperature, with different seeing condition, with a lot of mechanical things that can be a lot of factors that it will never be perfect, but you can reach the best with this. You can go toward the best, but maybe you can go infinitely to make better result. The things is having a feedback of your action. That's good things because the system is telling you are going in the good way, and if you are diverging, it will also give you some feedback. It's even better than the laser and things like this because the laser does not give you feedback. The only things that give you a good feedback is measuring the wavefront. Of course, there is also other method with devices like Schack-Hartmann, maybe you know that, or laser, which measure the it's interferometry, but it's very costly. It's $1,000 to buy one, and 10,000 or more amount to get Schack-Hartmann. And you don't have the possibility with the Schack-Hartmann to measure off axis and a lot of source. You have to stay on the center. It's difficult to measure off axis. Then what I recommend is doing that. First, before touching anything, is just make a screening of the quality of your telescope. You can take different stars, measure the result on different places. Check if the result is consistent, each measure. You can also move in different places on the sky, both sides of the meridian, different altitude, and check if the results are consistent. That means at this point you say, oh, mechanical things are okay, nothing move. And then once you are ready, you can start to fix the comma, if there is still comma on the center. Then afterward, astigmatism. And then once you are happy with the result, you can do a first check on the sky at focus on several images on a target, different target. And if you say, okay, that's okay with this, and then you can stop. Or if you see still some problem on the corner or you want to go further, you can then go again and check if there is a field, unbalanced field or sensor tilt. Sensor tilt is become relevant if you are F number 4 or below 4. Above this, it's not really a problem. Of course, it could be fixed, but it's not really a problem with a long focal ratio. For example, I have a tilt on my Takahashi, but it's a f5.3, and yeah, I don't change the, there is few tilt, but I don't manage the tilt with. I have a tilt corrector, but I don't go further to perfectly balance because it's nothing. There is no real impact on the images. And I think I'm done. I don't know if you have still question or.
Okay, we'll make some measures tonight. Just take some pictures and with defocused stars and see
Yeah.
what's
Yeah.
what it does. Yes. Just to see, and eventually I will send you I make some screen captures and maybe send you.
Yeah.
Okay.
Then, as I said, then defocus that value. Check the amount. If it's okay, you can go directly. Once you load your first image, you can check this bar.
Mm-hmm.
If even orange is okay. When it's red, it's not good. You can check if it's too much, it will go. If it's extrafocal, it goes up. And intrafocal, it goes down.
Okay.
Then you can just adjust a bit the focus if needed to go close to 0.
Okay,
then,
so I defocus for this amount of microns, and I have to the diameter of the defocus star must be 125 pixels.
Yeah, exactly.
Okay.
On your phase.
If it's not this value, what should I do?
You have to change the defocus to reach that value, because important is that value is not the real, because it depends the focus. I'm sure that with the Atlas it will be okay, because Atlas is very accurate.
Yes.
On my side I have Gemini from Optech. It's also very accurate. I'm always good with the Crayford. If you have a good one, normally it's good. You have maybe 124 or 26, but it's close to 25. If it's not exactly 25, it's not a problem. If it's 100 and you need 125, the system will not will give you an error message. I can show you.
Okay, so the important value is the defocus star diameter, but do I have to change the value of the expected defocus? If it's not, no, it will.
If it's intrafocal, yes, but normally most of the, because that's why we generate model extrafocal, because most of the people go extrafocal because they have enough mechanical travel on the Crayford.
We're on the middle of the travel, so we can go both.
It depends. Sometimes people prefer to be close to the telescope to avoid to balance the things, but it depends. If you are in the middle, you can choose, but it's better because the model is calculated extrafocal. It's better to stay with extrafocal direction.
Okay.
And then you can send me the result if you want, and then I can also take a look. Sometimes what I do when I do collimation is then I focus on the center star. And sometimes when you are late on the night, you are tired and you cannot take a good decision. Then I take back the day after and then I reanalyze the star. Sometimes I write report. I did that for the Italian telescope. Maybe I can show you where I put some analysis afterwards.